So last week we started this topic, bonding and structures. Just a quick revision, what we discussed last week. We started with ionic bonding, the bond which is formed by a complete transfer of electron. The metal tend to lose electron, where non-metal tend to gain electron. Metal will form a positive ion and non-metal will form a negative ion. And the electrostatic attraction between the unlike charges held together by a strong force. And this attraction is known as ionic bond, and the structure is known as the lattice. Ionic radii, as we discussed, for positive ions, the ionic radii, the positive ionic radii is smaller as compared to that of neutral atom because they lose electron. So they have more proton, greater nuclear attraction. That's why the size decreases. The positive ion is having smaller size as compared to atoms. But for negative ions, because it gain electrons, so negative ions, the size is bigger or larger as compared to that of atom because they have more electrons, same nuclear charge, but more electrons. So each electron experiences less force. That's why the size increases. This is what we discuss. If we have isoelectronic structures, like isoelectronic means if these ions have the same number of electrons, then we can compare the size of the ions such as nitrogen, oxide, fluoride, sodium, magnesium, aluminium. Enthalpy change of formation. What is the meaning of enthalpy change of formation? When elements form a 1 mole of a compound, that energy is called enthalpy change of formation. Atomization means when we form 1 mole of a gaseous atom, we call that as atomization. Enthalpy of ionization or first ionization and second, when we remove first electron from the atom, neutral atom in the gaseous state, we call first ionization. When we remove the second electron, we call that as second ionization energy. Electron affinity means when electron is added to a neutral gaseous atom, that's called first electron affinity. For non-metals, because they tend to gain electrons, so first one exothermic, but for second one it is endothermic. Why? Because oxygen, now it's oxide ion, negative, and electron is also negative, so like charges repel each other, so we have to supply energy to carry out the second electron affinity. So electron affinity, the first one is exothermic, but the second one is endothermic. We already discussed, that's why I'm quickly going through this part. Enthalpy of formation, when ions in the gaseous state will form a compound, we call that as enthalpy of lattice or the lattice energy. So trend in the lattice energy, when we compare the lattice energy, on which factors it depends. So lattice energy depends on the size of the ions. Size of the ions should be smaller as possible. Why? Because when ions are smaller, they're closer to each other, so they have strong attraction. Because like the metal tend to lose electron and the non-metal tend to gain electron. So the metal lose electron, the charge on the metal will be positive or plus, and the non-metal gain electron, charge will be minus. So if ions are smaller, they will have greater attraction as compared to a larger ion. If we have another ion, like example, a positive ion with the same charge and negative ion, because actually this positive ion, the nucleus is attracting the electrons from the negative ion. So because the distance is increases, so attraction decrease. That's why when we compare the lattice energy, which compound will have a higher lattice energy, A or B? So A will have a higher lattice energy because strong attraction, ions are closer, that's why higher lattice energy. And the second factor on which it depends is the charge of the ions. Greater the charge of the ions, higher lattice energy. Like example, if you have sodium chloride but you have magnesium oxide. Magnesium, already we discussed, the size will be smaller because it lost 2 electrons. So greater proton to electron ratio. And oxygen oxide, and both have the charge -2. There's +2 charge on magnesium and -2 charge on oxygen. So greater charge and smaller size. So they have a greater or strong electrostatic attraction. So the lattice energy of magnesium oxide will be higher as compared to sodium chloride. So the factor on which it depends on the size of the ions. The larger ions, the less negative enthalpy. Less negative means weaker attraction is there, so a small amount of energy will be released when ions will come closer. But if ions come too much close to each other, they release greater amount of energy, or strong attraction will be there. So as the ions are larger in size, become further apart, so it's a weak attraction. And second thing, the charge on the ions, so bigger or the greater charge on the ions result in greater lattice energy or more negative. So which one is having a higher lattice energy? Like which values, which shows that electrostatic attraction is stronger? -200, because lattice energy will always be negative because it's a bond forming. Bond forming is exothermic. -700. Which compound is having a stronger bond, a stronger lattice, higher lattice energy and stronger bond? So negative sign shows it is exothermic. So both reactions are exothermic. And the magnitude shows the strength. Higher value of a lattice energy, it means strong electrostatic attraction, so difficult to separate the ions from each other. Is it clear? The trend in the lattice energy, the comparison. Any doubt in this part? So when we compare the compounds, example, you're comparing, say, lithium oxide, or you have group 1 elements, which include, like, group 1 lithium is there, then sodium is there, then potassium is there, rubidium is there. So as we go down the group, the size increases. Size of atom will also increase, and the size of ion, because there are more electron shells are there. So size increases. So if I have a compound lithium chloride, sodium chloride, potassium chloride, rubidium chloride, so which one you think will have the higher lattice energy? Lithium chloride or rubidium chloride? Which compound will have a higher lattice energy? So lithium chloride will have a higher lattice energy. And what is the reason why lithium chloride is having a higher lattice energy? Because the ions, the lithium ions is smaller in size. Sodium a bit larger, potassium, and then rubidium. But the chloride ion is same because they are reacting with chloride. So the chloride ion is same for all, the size. So as you can see, the charge on the ion, this is lithium plus, iodine minus, chloride minus, sodium plus, chloride minus, potassium plus 1, chloride minus 1, rubidium plus 1. But this one is having a greater distance or a gap. So they have weak attraction. So as they have weak attraction, the lattice energy will be less exothermic or less negative, and this one will be more exothermic or more negative. Is it clear? Because the ions are closer, tightly packed together, greater amount of energy is released when these ions will come closer to each other. So to separate them, we need greater amount as well. And generally, like the order, the range of the lattice energy, like example for group 1 halide, like potassium fluoride, sodium fluoride, potassium iodide, they have a lattice energy in the order of about -700 to -1000. Group 2 halide having about -200 to -3500. And group 2 oxides have in the order of -300 to -4500 kilojoule per mole. Now, what we observe, like example, when we calculate the lattice energy, by using, there is a law which is called a Coulomb's law. You don't have to learn this law. So when we calculate the lattice energy by a Coulomb's law, which is also known as theoretical value, and when we calculate the lattice energy by Born-Haber cycle, the Born-Haber cycle was part of the syllabus before 2000, like 2018 syllabus. It was there, but not now. So you don't have to learn a Born-Haber cycle. Just there's a whole cycle is there, a method, a technique is there to calculate a lattice energy. So you will not find a direct calculation of this Born-Haber cycle. Just the idea. So using a Born-Haber cycle, when we calculate the lattice energy, that's called a practical value of the lattice energy. So what we observe when we are calculating a lattice energy by a Coulomb's law, and when we calculate a lattice energy by a Born-Haber cycle, which is a practical value, we find a difference between the values. What is the reason why we find a difference between the two values? Because, and like example, when we calculate by using a Coulomb's law theoretical value, example, if it is -600, but practically when we calculate for a same compound, we found it is coming out more than the theoretical value. So what is the reason why the theoretical value is smaller and the practical values are higher? The reason is because in a Coulomb's law, when Coulomb's law is applied, we consider ions are perfect spheres. That's our, the Coulomb law is only applicable by considering if we have ions, these ions or charges are perfect spheres. But in reality, in practical, ions are not perfect spheres. Ions are polarized. What is the meaning of polarized? That means distortion occur. They are not perfect sphere. So what happens, like example, if you have a positive ion, so if you have a positive and the other negative ion, so positive ion and negative ions, there's attraction between them. We call that as electrostatic attraction and ionic bond. But the electrons which are there in the outer shell, actually these electrons shifted towards the positive ion. So as these electrons shifted towards the positive ion, so you can see the distance between the two ions further decreases. As the distance between the two ions further decreases, the lattice energy will increase. So this is called distortion or polarization. So in reality, in practical, the ions are not perfect sphere. There is a polarization occur. Like the ions loses their shape, spherical shape, and they come closer to each other. as compared to when we calculate theoretically. That's why the practical lattice energy is always higher than theoretical lattice energy. If the two lattice energies are in the same order, like same values, it means because for some ions it does not distort, but most of the ion distortion occur, and distortion mainly occur for a negative ion, because negative ions are larger in size and the electron is attracted. Electrons attracted or move towards the positive ion, which result in a distortion or change in shape in the negative ion. And this distortion depends on the size of the positive ion. It should be smaller. The distortion, it depends on size of positive ion. To have a higher distortion, it should be smaller. It depends on charge of the positive ion. The charge of the positive ion should be greater so that it cause more distortion. And it also depends on size of the negative ion. The size of the negative ion should be larger so that it will have a greater distortion. So these are the factors which affects the distortion. Number one, the size of the positive ion, it should be small as possible. Number two, the charge of the positive ion, it should be greater so that cause more distortion or attraction towards the electron. And number three, the size of the negative ion should be larger so it will have a greater distortion. Is it clear why the theoretical lattice energy is not same as the practical lattice energy, or why there's a difference between the theoretical lattice energy and the practical lattice energies? Practical lattice energy is calculated by the experimental values are calculated by Born-Haber, whereas theoretical is calculated by a Coulomb's law. And we find there's a difference between the theoretical and practical lattice energies. Any doubt in this part? So you can see here the same thing which I explained just now, that if it is 100% ionic, there is no distortion. In that case, the theoretical value of the lattice energy and the practical value of a lattice energy will be same. But in practical, what happened? A negative ion, the electrons shifted towards a positive ion. We called as a distortion, or also known as covalent character of ionic compound. So when a compound have some covalent character, so what we'll observe, we'll find that there's a difference between the theoretical lattice energy and the practical lattice energy. Some properties of these ionic compounds. So physical properties, they have high melting point. What's the reason why they have high melting point? Because they have a strong electrostatic attraction and they have a giant structure which result in high melting point. Non-conductor of electric, like does not conduct non-conductor of electricity, because in a solid state the ions are not free to move. So if ions are not free to move, that's why it does not conduct electricity in a solid state. But in a molten or aqueous state, because these ions are free to move, so when we pass the current through a solution of ionic compound or a molten ionic compound, they tend to conduct because the ions are free to move. Brittle means when you apply a force, you can easily break the compound into part. we call that as a brittle, because the layers cannot slide over each other. Layers break when we apply a force. So how we can see the or observe that there are ions present, or how we can show that a compound, the ionic compounds contain ions and ions can move. So example, we have a compound which is called copper chromate. So this copper chromate, it contains copper ion which is +2 and chromate ion CrO4 with a charge -2. Copper ion is blue in color, where chromate ion is yellow in color. When we are passing a current, when we connect this to a supply and we are passing a current through it, so we observe the movement of the ions. What we observe? We observe the chromate ion, which are negative, attracted towards the positive terminal. So we will see near the positive electrode migration of the yellow ions or yellow color, or a yellow color is seen near the positive electrode. And copper is a positive ion, so attracted towards the negative plate. So we'll observe or see the migration of the positive ion copper, or observe a blue color near a negative electrode. So which shows that the ionic compound can conduct electricity in a molten or aqueous state. Same way, what we can do, we can also use manganese, potassium manganate. Potassium manganate is KMnO4, the compound, and it dissociate into K plus and MnO4 minus. Manganate ion is purple in color. So when we place this on a moist filter paper, so initially in the beginning we place it at this point. But when we pass the current, so we place it at this point. But when we pass the current, because the manganate ion is negative, so it is attracted towards the positive. So on the filter paper, we will observe the movement of the purple color, which shows that the manganate ion are attracted towards the towards the positive terminal, and their movement is visible. But because the potassium ions are colorless, so even though potassium or other ions, because they are colorless, even though they are moving, but we don't observe their movement. So this electrolysis of potassium manganate or copper chromate shows that the migration of the ions can take place, or ions can migrate or move from one place to another. Is it clear? This concept, how we can use electrolysis to locate the movement of the ions? Any doubt in this part? So the movement of the ions is observable, and we can say that the ions are moving and they are responsible for this movement or appearance of the color. Now we'll do some questions related to this topic so that it will improve your understanding. So this one is related to ionic covalent bonding and lattice energy. Covalent bonding we did not discuss yet, but we will discuss questions related to ionic bonding and lattice energy so that you have a better understanding of the topic. Okay, in this question, going down group 1 from lithium to rubidium, what we will observe? Which one is the correct answer? Everyone should participate in this because it shows your understanding of the topic. So ionic radius of atom decrease? No, it does not decrease, it increases because there are more electron shells. So as the number of electron shell increases, ionic radius increase, not decrease. The radius, sorry, atomic radius also and ionic radius, same trend is there for the first ionization energy decreases. So that's true because as the size is increasing, it will be easy. Ionization energy means energy required to remove electron from atom, neutral, gaseous. So if the size is larger, it will be easy to remove electron. That's true. Polarizing power increases. No, polarizing power decrease because to have a strong polarization, the positive ion should be smaller in size, polarization or distortion. That's why C is a correct answer. Is it clear? Everyone should participate in this so it shows your understanding of the topic. In the next question, drop of nickel sulfate, which is green in color. So this nickel sulfate, what it contains? It contains nickel. Nickel is a transition element, so it will be colored. And sulfate, nitrate, these are ions are colorless ions. So it placed in a moist filter paper in a slide. So the same thing, what we just discussed now, we have a moist filter paper. One side is positive, another side is negative. After 10 minutes, what we will observe? This one sulfate is colorless and this one is green. What we will observe? Yeah, C is the right answer. Why? Because green color, the nickel ion is attracted towards the negative terminal, where sulfate ions are, even though they are attracted, but their motion or movement is not observable because they are colorless. Magnesium oxide is, it's what? Ionic compound, metallic, ionic covalent, metallic and covalent. So it's ionic because metal and non-metal, so it's perfect ionic. Even it's perfect ionic or not perfect, but bonding is ionic. We call that as a covalent nature if distortion occurs. Look, in this question, you can see here, the lattice energy can be measured by using a Born-Haber cycle or calculated from electrostatic theory. Born-Haber is a practical value, experimental value, and electrostatic theory is a theoretical value in which we assume ions are perfect sphere. Lattice energy of magnesium chloride and magnesium iodide are shown. So lattice energy by using a Born-Haber and by using electrostatic theory are given. What does this data indicate about the bonding in magnesium chloride? So what it indicate about the bonding in magnesium chloride, or what it shows? It shows that it is not 100% ionic. Why it is not 100% ionic? From this data, how you can show? Because you can see that there is a difference. You can see there is a difference in the lattice energy. The lattice energy of by electrostatic theory and by Born-Haber, they are different from each other, greater difference. So what this data shows, it shows that the bonding we call ionic bonding, but we'll not say it is 100% ionic. Bonding is not 100% ionic. But if a question is there, like if they ask a question, if the question is what kind of bond is there in magnesium chloride, so you will mention it is ionic because metal and non-metal. But when you discuss in detail, it's not 100% ionic, slightly distortion occur in the negative ion. That's why you find a difference between the two values. Next part, they're saying why there's a greater difference in experimental and theoretical lattice energy of magnesium iodide compared to magnesium chloride. So when you compare magnesium chloride with magnesium iodide, so iodine is larger in size, greater in size. Magnesium is same. So magnesium ion is same here in both cases, but we have a chloride ion which is smaller in size, iodide ion larger in size because more. So which one you think will have greater distortion? Because you can see iodine is larger in size, so it is not able to hold its electron easily. So its electron shifted more towards magnesium, but chloride is smaller in size, so distortion will occur. That's why there's a difference, but less distortion because smaller in size, so its electron is still attracted by the nucleus of chloride, so less distortion. So the answer here, 1 mark you will mention iodide ion is larger. So more distortion results greater difference in theoretical value. I'm writing TV and practical value PV. Is it clear discussion? Then draw a dot and cross diagram to show the electronic structure of a compound magnesium. Only the outer shell electron, include the charges. So basically you have to draw magnesium chloride. So magnesium, the last shell, you can make it empty because it loses electron, or you can make 8 electron because that is now the valence. As the magnesium is 2, 8 and 2, so it loses the last shell electron, so it will be the second last now become the last shell with the charge +2. And chloride, so there should be 2 chlorine, and each chlorine should have 7 electrons of its own, and 1 it take from magnesium. So this will be the the dot and cross diagram for magnesium chloride. That you took in O level, so I just quickly go through this part. The second one, you have to draw a covalent structure. I'm not discussing covalent part because that we will discuss later. Suggests why the melting temperature of magnesium oxide is higher than magnesium chloride, even though both are 100% ionic. So it's of 3 marks. So what is the reason for that? Even it's 100% ionic. So what you can do, because the attraction between the ions affects the melting point. So why magnesium oxide is having a higher melting point as compared to magnesium chloride? So you can mention the first thing, because oxide has a greater negative charge, or you can mention greater charge density, like more charge in a unit volume. So strong attraction is there, or strong ionic bond. So required more or greater amount of energy to separate the ions from each other. You can also mention oxides ions are smaller in size, so they have ions are closer to each other, stronger attraction. That's why. So the answer for this part, when you write, you will mention oxide ions have greater charge density. Charge density means charge in a unit volume. You can see it has oxygen has greater charge -2 and volume is smaller. So that's why greater charge density. So strong electrostatic attraction, greater energy is required to separate ions from each other. Which of the following graph shows from left to right the trend in ionic radii for these isoelectronic ions? Nitrogen, oxygen, fluorine, sodium, magnesium, aluminum. What's the answer? Yes, what could be the answer for this one? Yeah, A is the right answer, because these all are isoelectronic and nitrogen. No, A is the right answer. All are isoelectronic. But what you have here, for nitrogen, 7 protons are attracting 10 electrons. For oxygen, 8 protons are attracting 10 electrons. For fluorine, 9 protons are attracting 10 electrons. For sodium, 11 protons are attracting 10 electrons. Magnesium, 12 protons are attracting 10 electrons. And 13 protons are attracting 10 electrons. So you can see more electron than proton, so each electron experience less force, so greater size. So nitrogen size will be larger than oxygen, oxygen size will be larger than fluorine, fluorine larger than sodium. Why? Because more proton, less electron, so each electron experience stronger force. And magnesium, 12 proton and 10 electron, so that's why A is a correct answer. Is it clear why A is the right answer?